This is why the universe you live in is not the peaceful backdrop it looks like from your backyard. Space has already ended one age of life on Earth, with a single rock the size of a mountain, has shorted out telegraph wires across 2 continents with a burst of solar plasma, and holds a black hole at the center of our own galaxy with the mass of 4 million suns. If any of that sounds like it belongs in a disaster movie, stick around, because every number in this video comes from published research and documented history, not speculation. Hit like and subscribe before we get into it, because what's coming next will change how you look at the night sky. Let's start close to home, because you don't have to leave the solar system to find genuine danger, and the clearest proof of that is buried under the Gulf of Mexico. Roughly 66 million years ago, an asteroid somewhere between 6 and 9 miles across slammed into shallow water off what is now Mexico's Yucatan Peninsula, traveling at around 12.5 miles per second. The impact carved out the Chicxulub crater, a scar roughly 110 to 120 miles wide, one of the largest impact structures ever found on Earth, and one still detectable today, only because geologists spotted circular patterns in magnetic and gravity survey data, patterns first noticed by geophysicists working for the Mexican State Oil Company back in the 1950s, though nobody connected it to a mass extinction until 1990. The devastation that followed was almost impossible to overstate. Researchers estimate the impact triggered the extinction of somewhere between 75 and 80% of all species alive on the planet at the time, including every non-avian dinosaur. Surface temperatures are estimated to have dropped by as much as 50 degrees Fahrenheit in the aftermath, as vaporized rock and debris blasted into the atmosphere blocked out sunlight for years, maybe decades. The physicist Luis Alvarez, who won the Nobel Prize for unrelated work, first proposed the impact theory in 1980, after noticing that a thin layer of clay, dating to exactly that period, found in rock formations around the entire planet, contained wildly elevated levels of the rare metal iridium, an element far more common in asteroids than in Earth's own crust. A decade later, researchers located the actual crater, and by the 1990s, the connection to the extinction of the dinosaurs was essentially confirmed. In more recent drilling projects, scientists extracted core samples directly from the crater's peak ring, deep underground rock pushed upward by the force of the impact, allowing them to reconstruct what happened almost minute by minute on the day it hit. Some researchers estimate the impactor released energy equivalent to billions of times the Hiroshima bomb, though the precise multiple remains debated. You don't need something that large to cause real damage, though, and we don't have to reach back 66 million years to prove it, because it happened again within the lifetime of most people watching this video. On the morning of February 15, 2013, a rock roughly 66 feet across, far too small to have been detected in advance by any monitoring system, entered Earth's atmosphere over Chelyabinsk, Russia, traveling at around 11 miles per second. It exploded in what's called an airburst roughly 14 miles above the ground, releasing energy equivalent to somewhere between 440,000 and 500,000 tons of TNT, on the order of 20 to 30 times the energy of the atomic bomb dropped on Hiroshima. The flash was, for a moment, brighter than the sun, visible from as far as 60 miles away, and the resulting shockwave, arriving minutes after the initial flash, shattered windows and damaged more than 7,000 buildings across 6 cities. Close to 1,500 people sought medical treatment, almost entirely from flying glass rather than the meteor itself, along with more than 180 reported cases of eye pain and around 20 cases of ultraviolet burns, similar to sunburn, possibly worsened by sunlight reflecting off the snow still on the ground that morning. Remarkably, no deaths were reported. Total property damage was estimated at around $33 million. It remains the largest object confirmed to have entered Earth's atmosphere since the Tunguska event of 1908, an earlier airburst over a remote, unpopulated stretch of Siberian forest, which was powerful enough to flatten trees across an area far larger than the blast zone at Chelyabinsk. Though because Tunguska struck a nearly empty wilderness, its human toll was almost non-existent by comparison. Researchers monitoring global infrasound networks, originally built to detect nuclear weapons tests, reported that in the years since 2000 alone, they had recorded roughly 24 atom bomb-scale asteroid airbursts entering Earth's atmosphere. the overwhelming majority over oceans or uninhabited land, unnoticed by almost everyone except the sensors built to catch far more serious explosions. That number should reframe how you think about the odds here. This isn't a once-in-the-history-of-civilization threat. It's something happening on a rolling basis, mostly out of sight, with Chelyabinsk simply being the rare case where an object of that size happened to come down over a city instead of an ocean, which is exactly why an entire branch of engineering now exists specifically to prevent it from happening somewhere it matters. On September 26, 2022, NASA's Double Asteroid Redirection Test, known as DART, deliberately slammed a refrigerator-sized spacecraft into an asteroid called Dimorphos, a small moonlet, roughly 560 feet across, orbiting a larger asteroid named Didymos. Neither object posed any threat to Earth. They were chosen specifically because Dimorphos was a close analog in size to the kind of asteroid that actually could threaten a city, and because its orbit around Didymos meant the effect of the impact could be measured precisely from telescopes on Earth. It worked. The collision shortened Dimorphos's orbital period around Didymos by roughly 33 minutes, and later analysis found the impact didn't just nudge the asteroid, it physically reshaped it, becoming the first time in history humanity intentionally and measurably altered the trajectory of a celestial object. It was, by any definition, a successful proof of concept for planetary defense as an actual, tested capability rather than a theoretical one. That capability is about to get a real-world audience. On April 13, 2029, an asteroid called Apophis, roughly 1,100 feet across, will pass within about 20,000 miles of Earth's surface, closer than many satellites in geostationary orbit, close enough to be visible to the naked eye from the southern hemisphere without any equipment at all. Current calculations, refined since Apophis was first discovered in 2004, show it will miss Earth safely, and NASA has stated that Apophis poses no impact risk for at least the next 100 years. But the flyby is close enough that both NASA and the European Space Agency are sending spacecraft to study it. NASA repurposing its OSIRIS-REx spacecraft to examine Apophis after the flyby, and ESA developing a mission called Ramses specifically to reach the asteroid before its closest approach, to observe in real time how Earth's gravity itself might reshape or disturb the asteroid as it passes by. It's a rare, genuinely useful cosmic coincidence. A large asteroid making a close, harmless pass, giving scientists a live rehearsal for exactly the kind of object planetary defense systems are ultimately built to stop. Now, asteroids aren't the only thing capable of reaching out from space and disrupting life on Earth without ever touching the ground at all. Sometimes the danger isn't a rock, it's the sun itself. On the morning of September 1, 1859, an English astronomer named Richard Carrington was sketching sunspots when he witnessed something no one had ever formally documented before: a sudden, blinding flash of white light erupting from the sun's surface, a solar flare. Roughly 18 hours later, a massive cloud of charged solar particles, a coronal mass ejection, slammed into Earth's magnetic field, triggering what remains, to this day, the most intense geomagnetic storm ever recorded. Auroras, normally confined to polar regions, were reported as far south as Cuba, Jamaica, and Honolulu. In parts of the northeastern United States, the sky glowed bright enough that people could reportedly read newspapers outdoors in the middle of the night. Gold miners in the Rocky Mountains were reportedly woken up by the light and started making breakfast, assuming morning had come. But the real damage hit the era's one piece of long-distance electrical infrastructure, the telegraph system. Wires acted like giant antennas, and the storm induced such powerful electrical currents through them that telegraph equipment sparked, caught fire, and shocked operators. In a detail that still amazes engineers today, operators in Boston and Portland, Maine, found they could disconnect their batteries entirely and continue sending messages back and forth using nothing but the electrical current the storm itself was pushing through the wires. The reason this matters today has nothing to do with telegraphs and everything to do with power grids. Modern researchers, including a widely cited 2013 joint risk assessment from Lloyd's of London and the firm Atmospheric and Environmental Research, have modeled what a Carrington-scale storm would do to today's infrastructure, and the estimates are staggering. Potential costs to the United States alone reaching into the trillions of dollars. with some worst-case assessments suggesting a full recovery of a badly damaged power grid could take years, since the large transformers that keep electricity flowing across a country are custom-built, expensive, and can take months or years to manufacture and replace if enough of them fail simultaneously. Smaller-scale versions of the same phenomenon have already caused real damage in the modern era. A geomagnetic storm in March of 1989 knocked out power across the Canadian province of Quebec, plunging the region into darkness. Experts remain genuinely divided on exactly how catastrophic a repeat of 1859 would be for a modern, technology-dependent society. But the underlying physics isn't in dispute. The same sun that keeps every living thing on Earth alive is also capable of firing an electromagnetic assault directly at our planet's technological infrastructure, without any warning beyond the roughly 1 to 3 days it takes a coronal mass ejection to cross the 93 million miles between the Sun and Earth. From threats born inside our own solar system, let's now widen the lens to something stranger, things that were never part of our solar system at all, and simply passed through. For most of scientific history, the idea of an object from another star system actually visiting our own was theoretical. That changed on October 19, 2017, when the Pan-STARRS telescope in Hawaii spotted an object later named Oumuamua, a Hawaiian word roughly translating to scout, or messenger from afar arriving first. Astronomers quickly confirmed it was moving on a hyperbolic trajectory, meaning it was not gravitationally bound to our Sun at all. It had come from somewhere else entirely, passed within about 24 million miles of the Sun, and was already on its way back out of the solar system for good, never to return. It was oddly shaped, estimated to be dramatically elongated, perhaps around 800 feet long, and only about 130 feet wide, tumbling through space at speeds up to roughly 54 miles per second. It showed no visible dust or gas trail the way a normal comet would, which puzzled astronomers, though it was later found to be accelerating slightly faster than gravity alone could explain, hinting at some kind of subtle outgassing after all. Less than 2 years later, in August of 2019, an amateur astronomer named Gennady Borisov, using a telescope he built himself, discovered a second interstellar visitor, a comet now called 2I Borisov, which behaved far more like an ordinary comet, complete with a visible tail, and which passed within about 180 million miles of Earth. Both objects are now gone, permanently ejected back into interstellar space. But their brief visits told astronomers something important. These encounters aren't as rare as anyone assumed. Researchers now estimate that at any given moment, there is likely at least one Oumuamua-sized interstellar object somewhere inside Earth's own orbital distance from the Sun, with roughly 10,000 such objects estimated to be passing through the solar system at any time, simply too small and too dark to detect with current telescopes, except on the rare occasions when one happens to line up perfectly with an instrument capable of spotting it. And interstellar objects aren't the only uninvited visitors theoretically capable of showing up. Some researchers studying planet formation around other stars have proposed that free-floating rogue planets, worlds ejected from their home star systems entirely and left to wander the galaxy in permanent darkness, may vastly outnumber the number of stars in the Milky Way, with some models suggesting the total could run into the billions or even trillions. A 2024 study went further, calculating that the Sun's own gravity is theoretically capable of capturing a passing interstellar object, or even a rogue planet, in much the same way planets like Neptune capture moons, and used known data on the roughly 130 stars and brown dwarfs in our solar neighborhood to estimate how often this kind of capture could plausibly occur. None of this represents any known, specific threat to Earth right now, but it means the solar system isn't the sealed, self-contained system it might look like from the outside. Things drift in from interstellar space more often than anyone assumed a decade ago, and every so often, one of them is large enough, or close enough, to be worth watching. Now, let's leave our own solar system behind entirely, and go to the center of the much larger structure that contains it, because everything we've covered so far is small compared to what's waiting at the heart of the Milky Way. Start with the number that's easiest to say and hardest to actually picture: 100 to 400 billion stars. That's the current scientific range for how many stars make up the Milky Way, and even astronomers admit the uncertainty is enormous. because counting stars in a galaxy you're sitting inside of is a lot harder than counting stars in a galaxy you're looking at from the outside. Our galaxy stretches somewhere around 100,000 light-years across, by the popular estimate, though a more precise measurement, called the D25 isophotral diameter, puts it closer to 87,000 light-years. Either way, light, the fastest thing in existence, would need tens of thousands of years just to cross it in a straight line. We sit about 25 to 28,000 light-years from the center, roughly halfway out, in a minor structure called the Orion Arm. And we're not standing still while we sit there. The entire solar system is racing around the galactic center at somewhere between 220 and 230 kilometers per second, which works out to roughly 515,000 miles per hour. At that speed, one full lap around the galaxy, what astronomers call a galactic year, takes something like 225 to 250 million years. The last time Earth was sitting in this exact spot in its orbit, the modern age of dinosaurs hadn't even begun. So on top of everything already covered, here's another uncomfortable fact. We are already moving at over 500,000 miles an hour through a structure so vast and so violent that we've only recently developed the instruments capable of understanding just how much danger is baked into it. Now let's go to the center of that structure, because that's where the real monster lives. At the heart of the Milky Way sits an object called Sagittarius A star, usually written as S**A star, and it is a supermassive black hole. Current measurements put its mass at somewhere around 4.3 million times the mass of our Sun, packed into a region small enough that its event horizon, the point past which nothing escapes, measures only about 16 million miles across. For comparison, that's smaller than the orbit of Mercury. It sits roughly 26,000 light-years from Earth, which sounds comfortably distant until you realize that's still well within our own galaxy, meaning it's not some far-off cosmic curiosity. It's the gravitational anchor that every star in the Milky Way, including our own Sun, is quietly orbiting right now. For most of the 20th century, astronomers suspected something massive and invisible was sitting at the galactic center, but they couldn't prove it. That changed through decades of painstaking observation, tracking individual stars as they looped around an apparently empty point in space. One of those stars, called S2, follows a 16-year elliptical orbit around SGR-A star, and watching its motion helped researchers pin down the black hole's mass with increasing precision. Then, in a discovery that reads almost like science fiction, astronomers found an even more extreme case, a star called S4714, that passes within just 12.6 astronomical units of SGR-A star, roughly the same distance that separates Saturn from our Sun. At closest approach, S4714 is moving at about 53.5 million miles per hour, which is around 8% of the speed of light, and it completes a full orbit around the black hole in under 10 years. Try to sit with that for a second. A star, not a spacecraft, not a probe, an entire star, whipping around a black hole fast enough that relativity itself becomes relevant to its motion. The work that confirmed SGR-A star as a genuine black hole was significant enough to win the Nobel Prize in Physics in 2020, split between astronomers Reinhard Genzel and Andrea Ghez for proving the object was a supermassive compact body, with physicist Roger Penrose sharing the other half of the prize for his earlier theoretical work showing that black holes are a natural, almost unavoidable prediction of general relativity. And then, on May 12, 2022, humanity got something it had never had before, an actual image. The Event Horizon Telescope, a global network of radio observatories working together as one giant Earth-sized instrument, captured the first picture of SGR-A star, a glowing ring of superheated gas wrapped around a dark central shadow. It's worth noting how difficult that picture was to take. From where SGR-A star sits, only about 1 in every 10 billion photons of visible light manages to reach Earth. Nearly everything else gets absorbed by the thick clouds of gas and dust sitting between us and the galactic core. Astronomers had to work almost entirely in radio waves, which pass through that dust far more easily, just to catch a glimpse of what's really there. Here's the part that might actually be reassuring, at least for now. SGR-A star is currently what astronomers call dormant. It's not actively devouring huge amounts of matter, and it only occasionally flares when it happens to pull in a stray cloud of gas or dust. But occasionally doesn't mean never, and one particular near miss in recent memory shows exactly how close a genuine feeding event can come to happening right on our cosmic doorstep, astronomically speaking. Back in 2011, a team led by astronomer Stephen Gillison discovered a strange object heading directly towards Score A star, a dusty, elongated cloud roughly 3 times the mass of Earth that researchers designated G2. Calculations showed G2 was on a collision course and that it would reach its closest approach, its periastron, sometime around 2014. As that date approached, astronomers around the world trained instrument after instrument on the galactic center. Because the prediction was dramatic, G2 was expected to pass within roughly 200 astronomical units of the black hole, only a couple thousand times the black hole's own radius, close enough that many researchers expected it to be torn apart entirely by the black hole's gravity, a process called tidal disruption, where an object gets stretched and shredded, essentially spaghettified, as one side experiences vastly stronger gravity than the other. Gillison himself described the cloud's distortion as it approached, saying it looked like a drop of milk in your morning coffee, with the leading edge of the cloud moving faster than the trailing edge as the black hole's gravity sheared it apart. Astronomers braced for a spectacular flare, a burst of radiation as shredded material spiraled into the black hole and heated to extreme temperatures on its way down. And then, in May of 2014, G2 made its closest approach, passing at a distance later estimated at somewhere around 36 light-hours from Score A star, and something unexpected happened. Nothing. G2 survived. It swung around the black hole largely intact, stretched but not destroyed, and continued on a shortened orbit, with no significant flare-up detected across radio, infrared, or X-ray observations. Follow-up research suggests G2 likely wasn't a simple gas cloud at all, but something with a dense, compact core, possibly a young star wrapped in a dusty envelope, or even the product of 2 smaller stars merging together, which would explain why it held together under the kind of gravitational stress that should have ripped a loose cloud to shreds. Researchers studying black holes have pointed out that events like this, called tidal disruption events, or TDEs, when they do go all the way to completion elsewhere in the universe, are one of the only ways astronomers can study a supermassive black hole's environment directly, since the black hole itself emits no light at all. Our own galactic center's brush with disaster turned out to be what one researcher called a cosmic fizzle, but it gave astronomers an unprecedented real-time rehearsal for exactly the kind of event that, elsewhere, ends far more violently. Now, from an object that survived its encounter with the black hole, let's talk about the stars that don't survive their encounters at all and get flung out of the galaxy as a result. Every so often, a pair of stars orbiting each other, a binary system, wanders too close to Score A star. When that happens, the black hole's gravity can rip the pair apart. One star gets captured and pulled toward the black hole. Its former companion, meanwhile, gets flung outward at a speed that can exceed 2 million miles per hour, fast enough in some cases to escape the galaxy's gravity entirely. Astronomers have confirmed at least 16 of these hypervelocity stars directly, and a broader study out of Vanderbilt University identified a group of more than 675 additional stars on the outskirts of the Milky Way, believed to be hypervelocity ejections as well. One particular case stands out. A star called S5HVS1 was discovered through the Southern Stellar Stream Spectroscopic Survey, led by astronomer Sergei Kopasov of Carnegie Mellon University. This star is moving at roughly 6 million kilometers per hour, about 10 times faster than a typical Milky Way star, and it currently sits around 29,000 light-years from Earth. By tracing its trajectory backward, Kopasov's team determined it had been ejected directly from Sagittarius A star roughly 5 million years ago. Kopasov himself put the timing into human terms, noting that the ejection happened, in his words, at the time when humanity's ancestors were just learning to walk on 2 feet. So somewhere out there right now, there's a star that was fired out of the center of our galaxy, around the same time our earliest bipedal ancestors were figuring out how to stand upright. And it's still traveling, still carrying that ancient kick from an encounter with a black hole most of us will never see. Not every hypervelocity star comes from the galactic center either. A separate discovery identified around 20 additional sun-sized stars moving at extreme speeds, but their chemical makeup matched ordinary disk stars rather than the composition expected from a close encounter with SGR-A star. That mismatch suggests an entirely different, still not fully understood mechanism is also capable of firing stars across the galaxy, possibly involving interactions with massive star clusters rather than the black hole itself. In other words, the galactic center isn't even the only slingshot in town. To be clear, the overwhelming majority of these rogue stars pose zero danger to us. A star like Kappa Cassiopeiae, roughly 4,000 light-years away, is never going to approach our solar system, hypervelocity or not. Space is simply too vast, and the odds of one of these ejected stars threading the needle into our specific neighborhood are vanishingly small. But their existence tells you something important about the environment we live in. The center of our galaxy is energetic enough and gravitationally violent enough to take an ordinary star and turn it into an interstellar cannonball, permanently expelled from the galaxy that made it. Now, from stars that get thrown away entirely, let's move to stars that don't survive at all, because that's where things get genuinely dangerous for a planet like ours, and where the historical record actually gives us something to work with. Supernovae, the explosive deaths of massive stars, happen across the Milky Way only a handful of times per century, which sounds rare until you remember how enormous the galaxy actually is. But here's something most people don't realize. We actually have a documented human record of these events. Historians and astronomers have identified somewhere between 7 and 8 confirmed supernovae visible to the naked eye across the last 2,000 years of recorded history. Each one a new star appearing suddenly in the sky, brightening dramatically, and then fading over weeks or months. The oldest of these was recorded in the year 105, observed by Chinese astronomers, and its remnant has since been identified. Another followed in the year 393. Then, in the year 1006, came what's still considered the brightest supernova ever recorded in human history, brighter than Venus, possibly rivaling a quarter of the Moon's brightness, visible across observers in China, Japan, the Middle East, and Europe. Less than 50 years later, in 1054, another supernova blazed into the sky, bright enough to be visible in daylight for weeks, an event recorded by Chinese and, likely, Native American observers. Its remnant is one every astronomy fan already knows, the Crab Nebula, the expanding cloud of gas that modern telescopes still study today. And at its center sits the Crab Pulsar, a rapidly spinning neutron star, the crushed core of the star that exploded, all that survived of it. A supernova in 1181 followed, then a long gap of nearly 4 centuries before the two most famous supernovae in Western astronomical history arrived within 32 years of each other. In November of 1572, a new star suddenly appeared in the constellation Cassiopeia, rapidly brightening to rival Venus itself. The Danish astronomer Tycho Brahe observed it obsessively for 18 months, and the event is credited with launching his career as one of history's most meticulous astronomers, someone whose later star position measurements would go on to help Johannes Kepler figure out the actual shape of planetary orbits. Then, on October 17, 1604, Kepler himself, once Brahe's assistant, witnessed his own supernova, describing it as similar in brightness to Jupiter with the color of a diamond, an event recorded not just in Europe, but in Korean and Chinese astronomical records as well, allowing modern researchers to cross-check the accuracy of observations made an ocean apart, centuries before any communication between those observers was possible. Kepler wrote an entire book about it, On the New Star in the Foot of the Serpent Bearer, reflecting on what a new star appearing in the supposedly unchanging heavens meant for humanity's understanding of the cosmos. Both the 1072 and 1604 explosions occurred in Tycho and Kepler's own lifetimes, meaning two of the most important astronomers in human history each personally witnessed one of the rarest events the sky has to offer, a coincidence of timing scientists still find remarkable centuries later. After Kepler's supernova of 1604, something odd happened. Nothing, at least nothing anyone noticed, for centuries. But the physical evidence tells a different story. Sometime in the second half of the 1600s, most likely around the year 1680, a supernova exploded in the constellation Cassiopeia, close enough and powerful enough that its remnant, known today as Cassiopeia A, is now the strongest radio source in the sky outside our own solar system, and the youngest known supernova remnant in the entire Milky Way. And yet almost nobody at the time seems to have noticed it happening. Historians have found exactly one possible record. The English astronomer royal, John Flamsteed, catalogued a faint, 6th magnitude star near that position on August 16, 1680, labeling it an ordinary star and never mentioning it again, because it was never seen at that location afterward. Modern astronomers now suspect Flamsteed may have unknowingly recorded the fading tail end of one of the most powerful explosions in the galaxy's recent history, simply because the star exploded behind a thick cloud of interstellar dust, dimming what should have been a spectacular naked-eye event down to something barely worth a passing entry in a star catalogue. Cassiopeia A sits roughly 11,000 light-years away, and today, its expanding shell of debris, rich in oxygen, sulfur, and iron, blasted outward from the dying star's core, is still visibly expanding at speeds between 4,000 and 6,000 kilometers per second, with a temperature in that shell reaching roughly 30 million degrees. Put those 7 or 8 historical supernovae together, spanning the years 105 through roughly 1,680, and you get a working sense of the actual pace of this danger. A genuinely spectacular, naked-eye stellar explosion inside our own galaxy roughly once every 2 to 3 centuries, based purely on the recorded history we have. And it's been well over 300 years since the last one. Purely on the numbers, in other words, we may already be due. Which brings us to the nearest candidate we actually know about today, Betelgeuse. Betelgeuse is the bright reddish star that marks the shoulder of the constellation Orion, and it's a red supergiant nearing the end of its life. Exactly how far away it is remains surprisingly uncertain. Different studies have placed it anywhere from about 500 to 724 light-years from Earth, a real scientific disagreement that hasn't been fully resolved. What isn't in dispute is that Betelgeuse is roughly 20 times more massive than our Sun, with a diameter around 700 times larger, and that it will, at some point, end its life in a supernova explosion. The timeline for that explosion is famously uncertain too. Most models suggest it could happen any time within the next 100,000 years, which in astronomical terms is basically soon. But a 2023 study by astrophysicists Evan Goldberg and Jared Bauer suggested the timeline might be dramatically shorter, on the order of mere decades, based on the unusual dimming and brightening Betelgeuse has been exhibiting since a strange event in 2019 and 2020 that astronomers now call the Great Dimming. Here's the good news, and it really is good news. Every distance estimate for Betelgeuse puts it well outside the danger zone. Even using the more conservative kill radius figures of 150 to 160 light-years, Betelgeuse sits at minimum 3 times farther away than that. When it finally explodes, models predict it will shine roughly as bright as the half-moon for several months, remain visible in broad daylight for close to a year, and stay visible to the naked eye at night for years after that. It will be, without exaggeration, the most spectacular astronomical event most of humanity will ever witness. And it won't hurt us at all. For a useful comparison, there's a supernova remnant called Geminga, believed to have exploded roughly 300,000 years ago from a distance of around 550 light-years, closer than even the most conservative Betelgeuse estimate. And life on Earth carried on largely unaffected. Right around the same period modern Homo sapiens were emerging as a species. But here's where the story shifts from theoretical to something that actually left physical evidence in the ground beneath our feet. Roughly 2.5 to 2.6 million years ago, something exploded close enough to Earth to leave a permanent signature. Scientists discovered this by digging into deep-sea sediment and finding elevated concentrations of a radioactive isotope called iron-60, a form of iron that isn't naturally produced on Earth and is created almost exclusively inside supernova explosions. The presence of iron-60 embedded in ocean floor layers dating to that period is, according to researchers, close to slam-dunk evidence that a supernova exploded somewhere between 100 and 150 light-years from Earth at that time. That's genuinely close, on a galactic scale. Close enough that physicist Adrian Mellott of the University of Kansas and his colleagues proposed a direct link between that ancient explosion and a marine extinction event happening around the exact same window in Earth's history, one that wiped out roughly 36% of coastal marine genera, disproportionately affecting shallow water species where radiation penetration would have been strongest. Among the possible casualties of that extinction, the megalodon, the giant prehistoric shark that had dominated the oceans until then. Melot's team published their findings in the journal Astrobiology, and their explanation for why coastal species suffered more than deep water ones is fairly intuitive once you hear it. Shallow water offers far less natural shielding from radiation than the deep ocean does. A creature living near the surface in coastal waters 2.5 million years ago would have been exposed to far more of that cosmic ray bombardment than something living in the crushing dark of the deep sea. More recent modeling, published in 2025, has actually refined this picture even further, suggesting the Iron 60 signature from that specific period could be traced back to one of two known nearby stellar associations, groups of related stars called Upper Centaurus Lupus or Tucana Horologium, either of which could plausibly have hosted the star responsible. That same research also found a second, separate Iron 60 spike from around 5 to 6 million years ago, suggesting our solar system may have been dealing with this kind of bombardment more than once during its recent galactic wanderings, not just as a single isolated event. It's worth quoting Melot directly here, because his own framing of the risk is refreshingly grounded. He said, "We have evidence of nearby supernova events at a specific time. We know about how far away they were, so we can actually compute how that would have affected Earth and compare it to what we know about what happened at that time." And when people ask him whether they should be worried about a supernova happening near Earth again soon, his answer is blunt. I tell them they should worry about global warming and nuclear war, not this stuff. There's nothing close enough to cause this kind of event in the very near future. Coming from the researcher who spent his career studying exactly this threat, that's about as reassuring a quote as you're going to find in this entire video. That ancient supernova, or more likely a whole sequence of them, is also believed to be responsible for something we're still living inside of right now, a region of space called the local bubble. This is a roughly 1,000 light-year-wide pocket of hot, thin gas that our entire solar system currently sits within. Researchers estimate it was carved out by somewhere between 10 and 20 separate supernova explosions over the past 15 million years or so, with our solar system having drifted into the bubble itself around 6 million years ago. We are, quite literally, living inside the aftermath of a chain of ancient stellar explosions. In a cavity, those explosions blew into the surrounding interstellar gas. Some researchers have gone further, proposing that the boundaries of the local bubble could actually reflect cosmic rays back inward when they strike its edges, extending the radiation exposure from any nearby supernova into what's been described as a cosmic ray bath, lasting anywhere from 10,000 to 100,000 years per event. If that's accurate, our position inside this bubble may have amplified the biological effects of that 2.5 million-year-old explosion well beyond what a simple straight-line distance calculation would suggest. Some scientists have taken the pattern even further, proposing that the solar system's motion through the galaxy itself, not just isolated supernova events, may correlate with long-term climate cycles here on Earth. As the Sun orbits the galactic center, it also drifts up and down through the galactic plane and periodically passes through the galaxy's spiral arms, denser regions where cosmic ray levels run higher than the surrounding space. Some researchers have speculated that these spiral arm crossings might trigger increased cloud formation and even contribute to Earth's ice ages, though this remains a genuinely debated hypothesis rather than settled science. A separate, similarly speculative idea proposed a 63 million-year cycle in Earth's fossil biodiversity linked to this same up-and-down galactic bobbing motion, though more recent research has leaned toward other explanations, like slow continental uplift, as a better fit for that particular pattern. The honest scientific state of this research is that the connections are intriguing, actively studied, and not yet proven. Now, from radiation drifting down from exploded stars, let's talk about something even more extreme. What happens when a star doesn't just explode, but explodes in a very specific, highly directional way? Gamma-ray bursts are, without exaggeration, among the most energetic events known to occur anywhere in the universe, arguably second only to the Big Bang itself in the sheer scale of energy released. They come in two categories. Short gamma-ray bursts last less than 2 seconds and are thought to result from collisions between compact objects like neutron stars or black holes. Long gamma-ray bursts last more than 2 seconds and are associated with certain types of exploding massive stars, specifically ones that have shed all of their outer hydrogen and helium before collapsing. Of the two, long gamma-ray bursts are considered far more threatening to any planet unlucky enough to be sitting in their path, because unlike an ordinary supernova, a gamma-ray burst isn't spread out in every direction. It's focused into narrow, incredibly powerful beams, meaning a burst could occur relatively far away and still cause catastrophic damage, provided Earth happened to be sitting directly in one of those beams. If a gamma-ray burst struck Earth from within about 10,000 light-years, which sounds huge, but is actually only about 10% of the galaxy's total diameter, the resulting radiation could severely damage the ozone layer and inflict enough cellular damage to kill off simple organisms like bacteria outright. And unlike an ordinary supernova, where the danger falls off predictably with distance in every direction, a gamma-ray burst's danger depends heavily on whether its narrow beam happens to be aimed at us at all. There are two known candidates inside our own galaxy that astronomers have specifically flagged as potential future gamma-ray burst sources, and both happen to sit at roughly the same distance from Earth, about 8,000 light-years. The first is a star called WR104, a Wolf-Rayet star discovered back in 1998 by University of Sydney astronomer Peter Tuthill. Wolf-Rayet stars are massive, extremely hot, and shedding their outer layers rapidly, which makes them prime candidates for producing exactly the kind of long gamma-ray burst described earlier. Astronomer Grant Hill told Forbes that WR104 could go supernova anywhere from tomorrow to 500,000 years from now, and that when it does, the gamma-ray burst and optical photons from the supernova would arrive simultaneously. Physicist Adrian Melott, the same researcher who studied the ancient supernova evidence, estimated that if a gamma-ray burst from WR104 did strike Earth directly, it could cause roughly a 50% increase in UVB radiation, with the first visible sign being a brief 10-second blue flash high in the upper atmosphere, followed by the actual damage. The second candidate is a system called APEP, nicknamed by researchers after the serpentine Egyptian god of chaos, located in the southern constellation Norma. APEP is a pair of extraordinarily luminous stars, and one of them appears to be approaching a massive supernova explosion. The discovery, led again by Peter Tuthill's team, was published in Nature Astronomy in 2018 and describes APEP as the first known candidate inside our own galaxy for producing a dangerous gamma-ray burst. The researchers were careful to note this remains genuinely uncertain territory, since no gamma-ray burst has ever actually been detected originating from within the Milky Way. Tuthill himself put it this way: ultimately, we can't be certain what the future has in store for APEP. The system might slow down enough so it explodes as a normal supernova rather than a gamma-ray burst. Current modeling, for what it's worth, suggests APEP isn't currently aimed at Earth anyway. To understand just how much energy we're actually talking about with gamma-ray bursts, it helps to look outside our own galaxy entirely, at an event called GRB 22109A. Detected in October of 2022, this was the closest and brightest gamma-ray burst ever recorded by astronomers, and even at a distance of roughly 2 billion light-years, unfathomably farther than anything inside our own galaxy, it briefly outshone the entire Milky Way as seen from Earth, and was powerful enough to measurably disturb our planet's upper atmosphere and lightning activity. Sit with that comparison for a second. A single stellar death, 2 billion light-years away, was strong enough to physically affect conditions in Earth's atmosphere. Now imagine, hypothetically, something even a fraction that powerful, going off 8,000 light-years away instead of 2 billion. That's the scale of catastrophe astronomers are talking about, even if, mercifully, the current evidence suggests neither WR104 nor APEP is currently pointed our way. Some researchers have gone as far as estimating the long-term statistical odds of a gamma-ray burst eventually triggering a mass extinction here on Earth, putting the probability at roughly 50% over the past 500 million years, and as high as 90% over the full 4 billion-year history of our planet. That's not a prediction of something imminent. It's a statement about deep time, the idea that across billions of years, in a galaxy this large and this energetic, the odds eventually catch up with you. And gamma-ray bursts aren't even the only kind of stellar object capable of hitting Earth with a wall of high-energy radiation from unimaginable distances. There's a stranger, quieter cousin to this threat, and unlike everything else in this section, it isn't theoretical. It already happened, in living memory, and scientists measured it happening in real time. On December 27, 2004, instruments across the solar system detected an enormous burst of X-rays and gamma rays sweeping outward from an object called SGR 180620, a magnetar, which is a specific, exceptionally rare type of neutron star with a magnetic field so extreme it defies ordinary description. Estimates put SGR 1806-20 somewhere on the order of 50,000 light-years away, on the far side of the Milky Way from Earth, tucked behind the galactic center itself. In the span of roughly 0.2 of a second, this single object released more energy than the Sun produces in about 250,000 years. The initial flash was so intense it briefly saturated detectors on satellites specifically built to measure high-energy radiation, instruments designed for far more ordinary cosmic events, and researchers found the burst was powerful enough to bounce measurably off the surface of the Moon. The flash was followed by a fainter, pulsating afterglow, lasting about 380 seconds, rhythmically flickering at intervals of 7.56 seconds, matching the magnetar's own spin rate. Here's the part that should genuinely surprise you. This event, from an object 50,000 light-years away, on the far side of our own galaxy, was strong enough to measurably disturb Earth's ionosphere and register a detectable signature in Earth's own magnetic field, picked up by multiple satellites monitoring our planet's magnetosphere, including one called CHAMP, which recorded a distinct, modulated disturbance timed precisely to the magnetar's flare. For a few brief moments, our planet's upper atmosphere behaved measurably differently because of an explosion of energy that had been traveling toward us since roughly the height of the last ice age, given how long light takes to cross 50,000 light-years. It's worth pointing out that magnetars like SGR 180620 are thought to be exceptionally rare, with only a small handful of similar giant flares ever recorded from the small number of known magnetars in our galaxy. And this 2004 event was, by a wide margin, the most powerful one ever measured, at least an order of magnitude brighter than the two previous giant flares recorded, in 1979 and 1998. If an event like that can leave a measurable fingerprint on Earth's magnetic field from 50,000 light-years away, it puts real numbers behind just how much raw power some of the most extreme objects in our galaxy are capable of unleashing, almost none of which we can predict or see coming in advance. Now let's step back from individual dying and exploding stars entirely and talk about a slower, quieter danger, one that doesn't come from an explosion at all, but from gravity itself, tugging on something at the very edge of our own solar system, echoing the interstellar wanderers we talked about earlier, only this time the danger comes from inside our own backyard. Surrounding our Sun, far beyond the orbits of the planets, sits an enormous, mostly invisible shell of icy bodies called the Oort cloud, containing an estimated trillions of individual comets. It's divided into two rough regions, an inner cloud made up of objects with smaller, tighter orbits, and an outer cloud extending vastly farther out. For most of their existence, these comets sit quietly, locked into stable, distant orbits, effectively frozen relics from the earliest days of the solar system's formation. But they aren't perfectly stable. They're subject to a subtle, constant gravitational influence called the galactic tide, which is essentially the pull of the entire mass of the Milky Way's disk acting on objects at the far edge of our solar system. Research published in the monthly notices of the Royal Astronomical Society indicates that this galactic tide is now considered responsible for roughly 90% of the mechanism that nudges long-period comets out of the Oort cloud and into orbits that can cross into the inner solar system, potentially putting them on a collision course with a planet. On top of that steady tidal pull, occasional passing stars can add an extra gravitational kick. A 2025 study examined one specific case, a star called HD 7977, which made a close pass by our solar system roughly 2.47 million years ago. The researchers modeling this flyby found it likely repopulated the inner Oort cloud with newly perturbed comets, and depending on exactly how close the star's approach was, their models showed the probability of a comet roughly a kilometer wide, striking Earth, increasing by as much as an order of magnitude, 10 times higher than the normal background rate, for a period afterward. What makes this particular flyby especially interesting is the timing. 2.47 million years ago sits remarkably close to the same window as that Iron 60 supernova evidence discussed earlier, meaning our solar system may have experienced a nearby stellar explosion and a comet shower triggering stellar flyby within a similar stretch of deep time, two separate galactic hazards converging on the same era of Earth's history. The idea that a passing star could trigger a wave of comet impacts isn't new either. It traces back to astronomer Jack Hills at Los Alamos National Laboratory, who calculated in the early 1980s that stellar flybys could shake loose Oort cloud comets and send them raining toward the inner solar system, and who even speculated, decades ago, that such a comet shower might have played a role in the extinction of the dinosaurs. To be clear, that's not the mainstream explanation for that particular extinction, the one we opened this video with. The dominant scientific consensus still points squarely to the Chicxulub asteroid impact as the primary cause. But Hills's broader point stands. Our solar system's outer edge isn't a sealed vault. It's more like a loosely held cloud of ancient debris, quietly vulnerable to the gravity of both the galaxy itself and any star that happens to wander close enough. Now, everything up to this point has been about individual stars, individual black holes, individual comets. But there's a bigger, slower danger too, one that isn't even about our own galaxy exclusively anymore. It turns out the Milky Way is, quite literally, eating its neighbors right now, while you watch this video. Astronomers have found direct evidence that the Milky Way has absorbed, or is currently in the process of absorbing, somewhere between 5 and 11 smaller dwarf galaxies over the past few 100 million years, based on streams of stars, gas, and debris still visible scattered across the sky, the leftover wreckage of galaxies that strayed too close to our own galaxy's much larger gravity and got torn apart. One of the biggest of these mergers happened deep in our galaxy's past. Using data from the Gaia Space Telescope, astronomers reconstructed evidence of a major collision between the young Milky Way and a smaller galaxy now called Gaia Sausage Enceladus, an event that occurred somewhere between 8 and 10 billion years ago. That ancient merger was so significant that roughly half of all the stars in the Milky Way's outer halo, the roughly spherical cloud of ancient stars surrounding our galaxy's disk, are now believed to be descendants of that long-vanished galaxy, meaning a huge portion of the oldest stars in our sky aren't originally ours at all. They're leftovers from something the Milky Way consumed billions of years ago. And this process never really stopped. Right now, in the present day, a smaller galaxy called the Sagittarius Dwarf Spheroidal, discovered in 1994, is actively being torn apart by the Milky Way's gravity, its stars and gas stretched into long streams that astronomers can trace wrapping across large portions of the sky. Researchers estimate the Sagittarius Dwarf will be fully absorbed into the Milky Way within roughly another 100 million years, meaning our galaxy is, at this exact moment, mid-meal on its smaller neighbor. Two other nearby dwarf galaxies, the Large and Small Magellanic Clouds, visible to the naked eye from the southern hemisphere and containing roughly 1 and 0.7% of the Milky Way's total stellar mass respectively, are also currently falling inward, expected to eventually merge with our galaxy as well, with some estimates for the Large Magellanic Cloud's eventual merger stretching out over the next several billion years. None of this poses any direct threat to Earth specifically. The dwarf galaxies involved are far too diffuse, and their stars far too sparsely spread out, for any of this to look like a collision in the way the word suggests. But it's a genuinely strange thing to sit with. Our galaxy has spent its entire multi-billion-year existence slowly swallowing smaller galaxies whole, one after another, and that process is happening again, visibly, right now, while astronomers watch. Which brings us to the biggest merger of all, the one most people have actually heard of, the eventual collision between the Milky Way and its much larger neighbor, the Andromeda Galaxy. Andromeda sits roughly 2.5 million light-years away, and it is not standing still. It's approaching the Milky Way, and has been for a very long time. In 2012, a team led by astronomers Roland van der Marel and Tony Sohn at the Space Telescope Science Institute used years of Hubble Space Telescope observations to track Andromeda's motion with unprecedented precision, and concluded that our two galaxies were on course for a direct collision within roughly 4 to 5 billion years. For over a decade, that became the accepted timeline, the widely repeated fact that the Milky Way and Andromeda were destined to merge. Then, in 2025, that certainty took a hit. A new study, published in Nature Astronomy and incorporating more recent Hubble and Gaia telescope data, went back and reran the numbers, this time accounting for the gravitational influence of two additional galaxies, Andromeda's companion galaxy M33, and the Milky Way's own satellite, the Large Magellanic Cloud. Once those extra variables were factored in, the picture became far less certain. The updated research found only about a 50% chance of a direct head-on collision within the next 10 billion years, with roughly just a 2% chance of it happening within that original 4 to 5 billion year window everyone had grown used to hearing. Lead researcher Till Sawala summarized the shift plainly. Even using the latest and most precise observational data available, the future of the local group of several dozen galaxies is uncertain. Intriguingly, we find an almost equal probability for the widely publicized merger scenario, or, conversely, an alternative one, where the Milky Way and Andromeda survive unscathed. In other words, one of the most repeated facts in popular astronomy, that our galaxy is doomed to collide with Andromeda, turns out to be closer to a coin flip than a certainty. And even if the collision does happen exactly as originally predicted, here's the twist. It probably wouldn't look like the destruction the word collision implies. Andromeda is estimated to contain around 1 trillion stars, and the Milky Way somewhere in the range of a few hundred billion. And yet, despite that staggering number of stars involved, the odds of any two individual stars actually crashing into each other during the merger are almost non-existent. Stars are so far apart, even within a galaxy's densest regions, that one widely used comparison describes it like spacing ping-pong balls, roughly 2 miles apart from each other. Even smashing two entire galaxies together, full of hundreds of billions of stars each, the objects themselves are simply too spread out to physically collide. What would happen instead is a slow, chaotic gravitational reshuffling, stars flung into new orbits, gas and dust compressed into new bursts of star formation. The two spiral galaxies gradually losing their distinct shapes and merging over hundreds of millions of years into a single new galaxy. One astronomers have already given a nickname, Milkomeda. And honestly, even that far future event might be moot for us personally, regardless of the exact odds. Multiple researchers have pointed out that the Sun's own gradual increase in brightness is expected to make Earth uninhabitable in roughly 1 billion years, and the Sun itself is projected to exhaust its usable fuel in around 5 billion years. Both of those timelines arrive well before, or right around, any potential Andromeda collision. As one astronomer put it, considering everything else already on the horizon for our solar system, a collision with Andromeda is, quote, the least of our cosmic worries. So, after everything we've covered, from the crater under the Gulf of Mexico, all the way out to a black hole with the mass of 4 million suns, where does that actually leave us? The honest answer is, exactly where we've always been, sitting on a small planet, orbiting an ordinary star, inside a solar system and a galaxy that are, by any measure, extraordinarily violent places. An asteroid ended the age of dinosaurs 66 million years ago, and smaller versions of the same kind of object still hit Earth's atmosphere with city-flattening force on what is, geologically speaking, a regular basis, most recently over Chelyabinsk in 2013. The Sun itself is capable of firing a storm of charged particles powerful enough to threaten a modern power grid, something it already demonstrated in 1859. Objects from entirely outside our solar system, like Oumuamua and Borisov, drift through on a routine, if rarely detected, basis. At the center of our own galaxy sits a black hole with the mass of 4 million suns, one that swallowed half of a doomed gas cloud's worth of drama in 2014 without so much as a visible flare. and that occasionally flings entire stars out into intergalactic space at millions of miles an hour. There are stars close enough and unstable enough to be genuine gamma-ray burst candidates, sitting about 8,000 light-years away, and a documented history of at least 7 or 8 naked-eye supernovae blazing across our skies over the last 2,000 years, roughly one every 2 to 3 centuries, with the most recent one arriving well over 300 years ago now. There's physical, buried evidence that a supernova exploded close enough to Earth 2.5 million years ago to possibly help end the reign of the largest predatory shark that ever lived. There's a magnetar 50,000 light-years away that once shook our planet's own magnetic field, with a flash lasting 1/5 of a second. There's a slow gravitational tide constantly nudging distant comets toward the inner solar system, with at least one documented stellar flyby that may have intensified that risk within the same ancient window as that supernova. There's an entire dwarf galaxy currently being torn apart and slowly swallowed by our own, right now, along with several more waiting their turn. And there's an entire second, much larger galaxy approaching us across intergalactic space, with a fate that current science genuinely cannot pin down with certainty. And yet, here we are. None of these threats are imminent. Betelgeuse is too far away to hurt us, whenever it finally goes. The supernova candidates that actually could produce a dangerous gamma-ray burst don't appear to be aimed in our direction. The last confirmed nearby supernova evidence is millions of years old, and the last visible galactic supernova in the historical record, while overdue by some rough statistical measures, still hasn't shown any sign of happening again. NASA's planetary defense systems, tested successfully in 2022, now exist specifically to intercept the kind of asteroid that could otherwise catch a city by surprise, the way Chelyabinsk did. The Andromeda collision, if it happens at all, is billions of years away, and won't even resemble the violent crash the word collision suggests. This isn't a video meant to make you afraid of the sky. It's meant to do something almost the opposite, to make you look up, whether at that faint band of light stretching across a dark, clear night, or simply at the sun rising the next morning, and actually understand what you're looking at. Not a peaceful backdrop, not decoration. A universe that has already reshaped life on Earth more than once, that is quietly eating its own neighboring galaxies, flinging its own stars into the void, and shaking our planet's magnetic field from clear across its own disk, all while we've been standing on this one small world, mostly without incident, and mostly, for now, without danger. That's the real story of how dangerous space actually is. Not that it should keep you up at night, but that it makes the fact we're still here, after billions of years inside it, genuinely remarkable. If this kind of deep dive into the scale and violence of the universe around us is something you want more of, make sure you're subscribed, because there's a lot more of it left to cover, and it only gets stranger from here.